We'll do a little bit of math now. If we assume the result of log normality of S of t, there's a sequence of conclusions we can draw from that are worth noting. So here we're going to assume this. This is by no means obvious, but it will be a result of some work that we will have coming. And if we assume that S of t follows geometric Brownian motion, equation 20.1, it turns out that that means the log of S at every point in the future has a normal distribution as specified here. Well, we can just do some algebra on this, and this means that the log of the ratio of St to S0 is normally distributed. All I have to do is just noting that the log of St divided by S0 is equal to the log of St minus the log of S0. You can see what I've done to shift the mean to the left-hand side. And then I can exponentiate both sides of this equation, and I get this final equation, which is a nice way of thinking about the probability distribution of prices, stock prices at time t, and that is stock prices at time t are equal to the initial price, S0, times an exponentiated normal. And the exponentiated normal has the mean we've seen before, the initial alpha minus the half sigma squared, again times t. It grows with t, and the variance is sigma squared t. So this is a nice way of thinking about what the probability distribution is of stock prices at every point in the future t, and that is that they're all exponentiated normals, which by definition means they're all log normally distributed. Now, the normal distribution itself provides an unrealistic description of stock prices, but it is a plausible model of continuously compounded returns, and indeed that's what we've seen by doing that little bit of algebra here. We're not assuming that St is normal. That would be ridiculous, since the normal distribution allows negative values of S. We don't want that. But here we're assuming that the returns, the return from time 0 to time t, that's what x is. X is a random return from time 0 to time t, that random return is normally distributed. That would seem to be a sensible model. And indeed, that's what we have, that we're modeling R of 0t, the return from time 0 to time t, as a normal distribution. And that'll allow us to say that, the ratio of prices between any 2 points in time are normally distributed. And why is that? Well, if we make this assumption that this is what S of t is, then this ratio can be expressed as e to the R0 t plus h minus R of 0t. And if I write that a little more neatly in the middle of the page, it's this ratio, let's call it St plus h divided by St, will be equal to e to the R, let's just call it t plus h, minus RT. Now, if RT is normal and RT plus h is normal, each of them is the normal variable of the normal return between time 0 and that time, then of course the difference between those two normal variables is also normal. And consequently, that's what this means, that if we assume that the return from time 0 to time t is normal for every time t, then it'll turn out by this simple algebraic trick that the return between any 2 points in time must also be normal, because the return will be a difference of normal variables, which we know is indeed normal. So in this derivation of the stock price behavior, and here we're just doing a little bit of background mathematics to motivate geometric Brownian motion a little bit more, and to motivate the model that it represents a little bit more. So let's imagine that we've agreed that we'll have these normally distributed returns. And as in the past, h is going to represent the length of a time interval. Intuitively, we're always thinking h is going to get small because we ultimately want to know the limit when h goes to 0. But think of h as a small time interval. And RH is going to be the normally distributed return. And let's assume that it has a mean of alpha h and a variance of sigma squared h. So RH is a period return. It's not an annual return, of course. It's a period return. And in the mean and the standard deviation of that period return, one sees the h. And then, therefore, alpha and sigma are annual values. So we then could model that st plus h, if we assume that there's a return, and here we're doing a multiplicative, more of an annual kind of return instead of a continuous compounded return, but this will motivate the result that we just saw. Here's a simple RH, it's a normally distributed return, and by assumption RH has that normal distribution.